Okay, this video about some of the clarification, some to the questions asked by some of you. So let hope I am able to explain this in this video. So this is mainly about the definition of multipole expansion in the Cartesian system. Uh, one of the question was why are monopole, dipole, and quadrupole in Cartesian coordinate system are defined in the way they are in the video, uh, and how the potential in the Cartesian coordinate get expanded using these multipole. Uh, so you have uh, uh, let us look at some of the physical interpretation and angular dependency. The concept of what is already said in the earlier video was that the concept of multipole moments are very similar to the uh, center of mass, moment of inertia, and so on. So we continue with the same idea. This concept is very useful with studying the extended objects such as a rigid body in the external force, or to study the potential generated by an extended object, uh, either charge or gravitational potential. Both works. The concept of moments uh, is usually defined with the weighted average with the distance from the center or origin. With the various powers, the weighted function gives taken as a various powers, you would get the higher moments. Um, so this is a very general concept. There is no much of potential or satisfying the Laplace equation in this case, and it can be applied to any physical quantities, mass, density, charge, probability, or any such functions. You can take higher moments of anything, almost anything. So and it has its own meaning in the given approach. So let's look at the uh, physical quantities such as a momentum, such as mass or charge density, and then we know that the monopole moment is defined as total of the charge or mass, and dipole moment is something like center of mass, or which you call a dipole in the case of electric field, but in the case of mass you call it a center of mass. And quadrupole moment also you can define with which you call the moment of inertia tensor, because it also has a trace. Trace is sometimes not convenient, it doesn't give any extra information, so you essentially make it a trace free, and that is what you call quadrupole moment, which is you call the trace free. Of course, you can have a higher moment, for example, octopole. You can define them. You can define them in a much straightforward way. You can have uh, with the trace, that is simply take the density multiplied by position with the three powers, and that would basically define multiple octopole moment. Of course, this is as trace have to be removed at this stage. It get a little messy because you have to remove trace along all the directions. So this is the standard meaning, and you are having a symmetrization. That means delta, or for any vector or tensor, symmetrization ijk, it means that half a ik plus half a ki. So this is with respect to two indices, and in the case of three indices, it's uh, just get a little complicated and lengthier. So let me write it here. What x I delta k j, it means that since the delta is already symmetric, oh, we have jumped a page back. Okay, here we are. So let me quickly go over this. Let me explain the quantity, the three symmetrization. So it's already symmetric about ijk. So you write xi delta kj plus 1 by 3 x k delta ji plus 1 by 3 x j delta ik. Of course, if it is not symmetric, if delta jk is not symmetric, then three more terms would be added by combining these factors. But in this case, this expansion would be sufficient and one can calculate octopole moment. I'm just giving because some of you asked about the octopole moment, so that's why I'm giving this definition. Uh, so that is this thing. Of course, let's look at the possible explanation with the electrostatic potential due to the charge distribution. So we have seen that given the charge distribution, using the Coulomb's law, we can define the potential. Uh, and of course, when x, the point at which you measure the potential, is far away from the charge distribution itself or outside the charge distribution itself, then you can expand the distance 1 by x minus x prime in terms of binomial or Taylor expansion in various powers of x minus x prime. So this is what essentially leads to multipole expansion. So you have this is simply you can do some calculation and figure out the multipole expansion. It's not too difficult. Binomial expansion is pretty simple, and one finds out that the potential is given by this equation where you have monopole term, dipole term, quadrupole term, and many more terms which we call octopole and so on. So this naturally gives you the potential. This is 1 by r here, and 1 by this is a dipole potential which you have r square x x. This is a unit vector here, and same way quadrupole moment, and you see that it is already defined as a trace-free tensor, which is naturally coming out from the expansion. So this is how you express the potential for the each term, and of course there is no much fuss about it. It's just a Taylor expansion of the potential uh, around point charge. Of course, let's look at the good old example. What we have seen that we have three charges, two positive charges, displaced at a distance symmetrically about z-axis from the origin, and at a distance d, and minus 2q at the origin. Of course, monopole term is 0. We have seen that dipole term is also 0, because you can view this as two dipoles which are placed uh, one this way and one this way, and their sum adds up to 0, and there is no total effective dipole moments. Quadrupole moments we calculated, and you get this term. Can this have a higher multipole moments? We have seen that unlike spherical polar multipole moments, Cartesian, the system which we have intelligently designed such that it has only quadrupole moment and no other quadrupole moment. Of course, you may think that you need to check it, however, so you can test it, but it is not very simple to compute this. Um, all those things have to be computed, and octopole moment has to be computed given by this formula. You see that for each charge, you essentially have to compute the multipole, octopole moment, and then you sum them up over all the charges. Of course, it's a bit of a long, tedious calculation. There is a possibility that you or me could make a mistake. So I had to spend some time, and then finally decided to do it on the Mathematica, write a simple code to compute the octopole moment of a given charge distribution, and then you see that this actually has zero higher octopole. So if some of you have calculated, please do check it again. It is a long calculation, so it is a possibility of making some sign error or adding up here and there could be an issue. So I have checked and convinced myself that there is no higher octopole moment for this system. Okay, let me stop here, and we'll continue with the other this thing.